Hello everyone, welcome to the Dandelion Chemistry series. My name is Yanzeng or Steve Go, and today's video will be dealing with atomic structure, chapter 2 in the syllabus. Although I said that I'd be following more of the units than the Oxford guide I used in the intro, I figured that the study guide would have a more organized structure of the units that I liked, so the units will actually be more organized in the order of chapters. With all that said, let's move on to the content. First, let's start with introducing the atom, which I personally like to call the smallest recognized particle of a chemical element. Atoms are consisted of protons, neutrons, and electrons. Protons and neutrons reside within the nucleus, while electrons exist somewhere around the nucleus in different energy levels and move around. Protons are positively charged, and within the nucleus, they are held together by neutrons, which don't have charge, which attract both themselves and the protons to stabilize the nucleus because protons repel each other because they have the same charge. The number of protons decide which element the atom is and becomes the standard for deciding how elements are lined up on the periodic table. Electrons are negatively charged, with its size and mass being substantially smaller than that of the protons or neutrons. This becomes important because of the calculation of the mass of an atom. Now, we use something called mass numbers to compare the masses of atoms or ions, which you would have probably learned by now that they are charged particles created through the loss or gain of electrons. The mass number of a particle is calculated by the total sum of the number of neutrons and protons, since they are of approximately the same mass, and electrons are just too small, so they can be ignored. The shorthand form looks like this, like the picture over here, with the mass number and atomic number on the left, and if there is any charge, meaning it's an ion, it's written on the top right corner. There are cases where the mass number and atomic number are switched. If that happens, the bigger one is the mass number, since the number of neutrons are added to the number of protons, which is the atomic number. Now, let me introduce the concept of isotopes. Isotopes are variations of the same element that contain equal numbers of protons but different numbers of neutrons, having the same chemical properties but different masses. The important thing to know here is because the number of neutrons are different, a single element can have different mass numbers for its atoms. Because isotopes exist, when we want to talk about the mass of atoms, ions, or the particles that are made when they come together, we use relative atomic mass, which is the weighted average of all isotopes' mass numbers. Here, weighted means that the percentage of abundance of each isotope is multiplied to its mass number. So, for example, here we have 3 isotopes of silicon. So we add up 28 times 92.2%, 29 times 4.7%, and 30 times 3.1% to get a total of 28.09 down here, as you can see in this part of the periodic table. Okay, so we talked enough about the nucleus, so now let's talk about electrons. More specifically, we're going to talk about where they are. The concept we use to explain this is orbitals. Orbitals, or the definition I like the most of them, are representations of patterns or places where electrons are most likely to exist. So within an energy level, which was probably referred to as an electron shell till this point, there are different sublevels, S, P, D, F, and there's more like G, H, and I, but we don't care about the rest. And here's how they look like. The s orbitals up here look like spheres. The p orbitals are the 3 under the s orbitals, and yes, there are 3 of them. The d orbital, we have 5 of them, again underneath the p orbitals over here, and we have the f orbitals on the left. There are 7 of them. Remember that each of these types can contain 2 electrons. So as you progress up the energy levels, you're basically placing bigger versions of these on top of one another to represent where the electrons probably are, with the first energy level including only the s, the second s and p, the third s, p, d, and the fourth s, p, d, f, and so on. So with that in mind, we're going to look at orbital diagrams, which are basically a way of expressing where the electrons are and look like these 2 diagrams over here. So each horizontal line represents one sublevel, and underneath the groups of lines are descriptions for which sublevel you are looking at, like 1s, the s orbitals in the first energy level, or 3p, the p orbitals in the third energy level. They are arranged in order of how much energy they have. Electrons are arranged following these three principles within these diagrams. The first one is the Aufbau principle, which states how electrons occupy orbitals of lower energy first. Hund's principle, which states that electrons occupy orbitals singly before pairing up. And the Pauli exclusion principle, stating how each orbital is occupied by two electrons with opposite spins. For example, let's look at iron over here, number 26. The electrons occupy in order 1s, 2s, 2p, 3s, 3p, 4s, and 3d. Normally, the energy level is higher when the energy level is higher and gets higher within the same energy level, from S to P to D to F and so on. However, 4s is sort of an exception due to the fact that 4s orbital is a little lower than 3d orbitals, meaning it gets filled first, according to the Aufbau principle. According to the Hund principle, as you can see in the 3d orbital, the blue electrons first fill each orbital, then the other red electrons with other spins starts to get introduced. Finally, each sublevel only has a maximum of 2 electrons according to the Pauli exclusion principle. If you look down here, copper has its 3d orbital filled before the 4s orbital is filled. This is due to the 3d orbital having one electron in each orbital, in like chromium, or 2 like you see here in copper. Those two cases, it's more stable to fill these rather than filling the 4s orbital first. So these two are exceptions you need to know. Now we're going to look at the electromagnetic spectrum. Now, why the electromagnetic spectrum, you may ask? Now, it's because we need to look into the movement of electrons across different energy levels in relation to the electromagnetic spectrum. What you basically need to remember over here is that the shorter the wavelength is, the stronger the energy it contains. When electrons move across different energy levels, they emit or absorb different wavelengths of energy according to whether they move to an energy with lower, which is emission, or higher energy, absorption. And how the different places they move to is in terms of energy. A way to visualize this is through emission light spectrums, which basically tell you which wavelengths are emitted when the electrons move to lower energy levels, and the opposite case, which produces absorption light spectrums, since they need energy to move up energy levels. There are questions that ask you the difference between emission light spectrums and continuous spectrums up here, so keep in mind that continuous spectrums are of all wavelengths, while emission line spectrums only include certain wavelengths. Now let's look at hydrogen's emission spectrum. First, we have 3 types of emitted wavelengths we are introduced to: the Lyman series, the Balmer series, and the Paschen series. These 3 groups are each the result of an electron being placed in the first, second, and third energy levels, respectively, each losing energy through the emission of the Lyman series ultraviolet radiation, the Balmer series visible light, and the Paschen series infrared radiation. An important thing is that the emission spectrum shows, an important thing that the emission spectrum shows is that as wavelength decreases, the gaps between the lines are smaller, as you can see over here, suggesting how higher energy levels have less of a difference when it comes to energy. So the last major part we will look at right now over here is ionization energy, or the energy it takes to remove electrons from atoms or ions. As we discussed above, you need to give the electrons energy for them to break apart from the particle. Ionization energy is decided by three factors. The first is the distance from the nucleus, which states that as electrons get closer to the nucleus, the attraction between them increases, increasing the energy requirement to get them apart. This differs the most depending on the number of energy levels. The second is nuclear charge, which is nuclear charge, where the higher the nuclear charge, the more energy is needed to separate the electrons since the attraction is stronger. The final one is the shielding effect, which basically shows how the repulsion of electrons in the lower energy levels lower how much energy is required to separate the outside electrons from the particle. So the general trend for first ionization energy, the energy needed to remove the outermost or higher energy electron from a neutral atom in the gas phase, is that it decreases down a period and, it increases down a period and decreases down a group. In the same period with the same number of energy levels, the shielding effect and the distance are similar between elements, but the nuclear charge increases as we progress through a period, thus increasing ionization energy. In case of groups, as the number of energy levels increase as we progress down a group, the number of shells increase, increasing both distance and shielding effect more than the increase of nuclear charge can catch up for, meaning that there is a decreasing trend for ionization energy down a group. So, that is all from Dandelion today. If you have any questions, please comment down below. And if you would like to stay tuned for further videos, please click subscribe. See you next time.